So I hope I won't lose my voice during the talk. So my name is Aivars Kalvāns, and I will talk about shared database concurrency, and I will explain what it means after a few slides. So first, I work for Tieto Latvia, and especially its payment card business unit, and we are quite different from the rest of the Tieto, and that we are a product-based company, not a we don't offer services. And I started about 13 years ago as junior developer, and then I became a software architect. But I still do write some code, although it gets less and less code every year. So, and what we do is we build a payment card system that is used by about 400 financial institutions in about 30 countries, and it processes hundreds of transactions per second in online mode, and thousands of transactions per second in batch mode when it's processing files. So, and these are financial transactions or financial events, so don't confuse them with the database transactions. So, and to achieve this, obviously we need some concurrency. And so the most common topic is something about shared memory concurrency, where you have multiple processes that all communicate by modifying some shared memory locations. And the most typical way of this is multiple threads, and also it's possible by using processes and something like POSIX shared memory API. And if you were present at the previous presentation, you all should know by now that this is a really bad idea. So there's a lot of buzz, and there are a lot of popular topics and articles about lock-free algorithms and data structures, and different approaches to concurrency, like actors, and also using functional programming for concurrency. And this is all very interesting, but if you look at typical architecture of an application, you will notice that this covers only the middle layer, where you have the business logic. And it's somehow good because we introduced this middle layer to take the load off of the database. So, but obviously, so most applications still use a database, and if you have a database, it's very likely that the database is the bottleneck of your application. And what's even more interesting is that you might not know that the database is the problem, because if you experience concurrency problems, what you typically see is a larger response time, but you don't see the breakdown that it took, for example, 10 milliseconds to wait for other processes to complete and only 1 millisecond to do the actual work. To see that, you have to go and check for some database metrics, and as developers we usually don't do that. So that's why I want to talk about shared database concurrency, and I use the same definition as shared memory concurrency. I just replace the memory with a shared data in a database. And when I first was learning about databases and started to use them on a project, then I had this impression that there's some wizard called DBA who comes in when you have problems and solves them by doing typing some magic on a keyboard. But well, I quickly realized that that's not the case. So I'm really happy that in recent years there's this Oracle Real World Performance team, which consists of top database experts, and they go around the countries, and they have this full day demo where they show how things like number of threads or number of connections in a pool and like load balancing, how they influence performance. So, and one of the key things, key messages is that most of the performance problems come because we use the database incorrectly. And they also talk about that DBA or a new hardware can get you a 2x performance improvements if you are really lucky. But to get something like 10x improvements or 100x improvements, you really need to change your code, you need to change your design, and you need to change your algorithms. So, one thing is clear, that you must learn about what's happening in a database. If you do a Google search, most likely you will come up with pessimistic locking. And this is like really old school. This is what you do if you to prevent like concurrent updates on some data. There's also something called optimistic locking, which you use when you don't expect frequent concurrent updates. And of course, if you do this in year 2014, you will find that you can use NoSQL to avoid all the concurrency and scalability problems. However, there are good and bad reasons for choosing NoSQL, and like this is a really bad reason for choosing NoSQL, and you can do that, but like you can choose some NoSQL database, but you need to understand what are the reasons you chose it, and what are the reasons that like relational database didn't fit your problem. And it's true the other way. If you choose a relational database, you must understand which parts of the NoSQL didn't fit your problem. And I decided to add this slide after yesterday's keynote, because like banks don't use transactions. Like we don't need relational databases with transactions. So the truth is, yes, banks really don't use transactions, but it's like the visible tip of the iceberg. So banks don't use transactions to cover or to cover everything from the ATM up to the client or card record in the database, but they still use transactions. And what's more important, there's really a lot of code and a lot of computing power devoted, and even manual work just to make it work without transactions. So to give you an idea, so the most common case most of you have seen is that you have some money reserved on your bank account for 2 weeks or a month. So, and this is a direct result from banks not using transactions. So while it can work, it's not exactly great for you as a customer, and not many of us are happy about the situation. So yeah, banks don't use transactions, but it doesn't necessarily mean that it's the best way to do that. So, and the question is there anything else beside this pessimistic locking and optimistic locking? Well, since we use Oracle database, the obvious way was to go and learn what the Oracle database offers. So, like you can lock a table in Oracle database, but that's not interesting for concurrency. What's more interesting is that Oracle uses row-level locks internally to ensure that databases have this ACID guarantees. And the most important thing to remember here is that locks are released when transaction is completed using commit or rollback. And there are other things in Oracle like that selects don't block any updates to the data, and updates to the data don't block any selects from the data. So so the only way you can get two transactions waiting on each other is if you have two updates. So what it means practically is that you can place a row level lock by using select for update. So this is typically your pessimistic locking. What's interesting about Oracle is that it offers this no wait option. So you can try to take the lock in non-blocking mode. If the lock can't be taken, you get back quickly. So obviously, update and delete statement takes a lock, and therefore they might block and wait on the other transactions. What not so obvious is that insert statements might block as well, and this happens if two insert statements are going to violate some like unique constraint. And this is something that was like a bit surprising in practice when we saw such cases. So just to talk about, okay, yeah. So, and this is, we obviously need a name for this, and I will call it implicit locking. That's something that the database does behind your back, just to ensure the correct work. And what do other databases do? Well, there are like different kinds of solutions. Postgres uses row level locks just like Oracle does. With MySQL, it's very complicated because it depends on which backend you choose for the database. So it can be either table level locks or block level locks or row level locks. Other databases like DB2 allow you to select what kind of locking you want to use on a specific table. Another thing you must learn about databases is what isolation levels they offer. And so this is like, so the main takeaway from this is that it's not possible to write a generic code that performs well on any database. If you want a good performance, you must learn what your database provides, how it's implemented, and only then you can use those specific features to achieve good performance and scalability. And so now we are left with three locking options. Of course, you have question which one to use. But first, let's look at the differences. So, okay, it's visible. So, the pessimistic locking starts with a select for update that takes a lock on the data. Then the user modifies the data. It does update in the database and then it commits. So, in this red arrow shows how long the locks are held in the database. So, obviously, they are released when the commit is made, but the lock in this case starts with a select. Well, optimistic locking is a bit different. By using select, you select some version of the data and you use this version in update to ensure that nobody has modified the data between you reading it and you updating it. So, and then this update places a lock on a row, or it actually may fail. It may update 0 rows, in which case you do a retry of this update. So you basically go read the version of the data again modify it and do update, and you do that until you succeed. So, and then there's like implicit locking. It's really similar to optimistic locking with the single exception that it doesn't verify that the data you are updating is the same one you read before. So I will discuss in next slides. Implicit locking might lose some updates. So, and then there's this is the article that you come up with when you look for optimistic and pessimistic locking in Oracle. And so it's like pretty serious site called Oracle FAQ, and it talks about how nice and wonderful optimistic locking is, and it gives you impression, if you still use pessimistic locking, that you are a fool, and you should really try to use optimistic locking as much as possible. And this article also highlights problems with pessimistic locking, and it promises that optimistic locking solves those problems. So I will look at some of those problems. So the first one is the lockout problem, and it's like when you do place a lock on a row, and then you go to have a lunch, and then nobody else can modify the same data until you come back and do commit or rollback. But the thing is, since as I showed you in table before, both optimistic and pessimistic locking do take locks, so there's really not much different if the lock was placed with the select statement or update statement. There's still a lock involved, and you can still go to lunch between placing a lock and doing a commit. So the other problem is deadlock problem. So it's often claimed that optimistic locking solves the deadlock problem, but in reality it does not, because there is no difference between placing locks by using select or placing locks by using update. If you place two locks using select and place two locks using the update, you might still mix the order and you get a deadlock. Then there's some articles claim that optimistic locking has a better performance, but so the table showed that basically each locking does a select and update, and there's really not much difference between doing select and update. If you see difference, that are probably some minor changes, and you won't get like 2x difference. So the question is, why does optimistic locking exist, and does it have some good features? Well, the obvious feature is that it holds the lock for much shorter time than pessimistic locking does, and this is a good thing. A good thing if you first think about it. But if you remember that optimistic locking is used when you don't expect concurrent updates on the data. So if you don't expect concurrency, I think that it doesn't matter how long you hold the locks. It only matters when you have a lot of concurrency on single row. Another thing that's not visible is that update will wait for other sessions to release the locks before it tries to execute the statement, and this is imagine the situation: you have 10 sessions that try to update the same row. So basically all those 10 sessions are put into the queue. So the last one, the 10th, waits for 9 sessions to complete before it even tries to check if the version of the data is the same. Now the first one does a commit, and in theory the last one should know that it's trying to update the wrong version of the data, but it doesn't know that until the queue is empty and all other sessions before it have completed their work. So that was we tried to write a software using optimistic locking, and this is the problem where it broke down. So, but the one thing that optimistic locking solves is problem of lost updates. So what happens is that there are two kinds of updates. There's an absolute update where you set a field to a new value. And this is a typical example you have in your optimistic and pessimistic locking articles, where you set a new salary for employee. So now, obviously, the last update stays. So the updates before are lost by the new update. But like not all updates are like that. There are also relative updates where the order you apply the updates doesn't really matter. So and this typically is adding a positive or negative number to some counter. And in our business, this is your bank account or card account. It doesn't matter in which order the transaction amounts are applied to your account. The amount will still be the same, with the exception of like if you have some complex fees for your credit cards. And also calculating like minimal and maximum value is also a relative update, and it doesn't matter in which order they happen. So and the optimistic locking is really a good tool if you have absolute updates. For relative updates, you are good by using like implicit locking. So yeah, so how to choose the locking methods? So basically, I would suggest try to use implicit locking by default. That is, don't perform any pessimistic locking, don't add version numbers to your data. So just do a relative update. And also for some updates, it's okay that you lose the updates in between. Yeah. So then you can use pessimistic locking to prevent concurrency at all. I don't know a lot of cases, but I have seen a couple of those, and mostly for historical reasons. And I really don't know a good use for optimistic locking. Oracle has something like transaction isolation level, where you can say it's serializable. And in that case, you don't have to change any code, and your transaction will be executed in isolation, and it will behave similarly to optimistic locking, except you won't have to do any retries. No, you won't. You will have to do retries, but you won't have to add like extra columns to your data, and you won't have to write code and update statements to check that the data is still the same. So if you think that optimistic locking is for you, then maybe better try different transaction isolation level. So and now I want to talk about ways how to increase concurrency. So once you have chosen your methods of locking, there are still a lot of things that a developer can do. And I will go through a list of things, and in practice we use almost all of them simultaneously. So the basic idea is the same as in programming with locks. So you want to reduce the time locks are held. The next thing is you should try to reduce the need for locks. That is, you should minimize the amount of data you update. And then you can do something like fine-grained locks. Oracle database really doesn't give you that, and most databases don't give you that. But I will show example at the end how we do this. So for warm-up, let's start with like a couple of simple examples. I hope that everyone is using prepared statements, but the real life situation is that people are not using them because there are still SQL injections in practice. And once a year I see like manually creating a SQL statement even in our code base. So then there's something, this is specific to Oracle, but again I think most databases do this, is that database has to parse the SQL statement, and when it does it the first time, it's called hard parse, and then it stores it in cache. And then when you parse it again, it will take it from cache, and this is called soft parse. most recommendations say that you should avoid hard parses. For our software, we say that you should also avoid soft parses. That means that if you create a statement once, you keep it in some class variable or just in some application level cache, so you don't go to database cache to retrieve the statement again. So the next thing is to do batching or bulk operations. So if you have a databases are great to work on sets. Unfortunately, not all databases offer this feature, but in Python, but anyway, you should try to use the API for that. So in Python, it's execute many, where you give a SQL statement and then give a data for multiple rows. And what it should do is that it sends the statement to the database once and sends all the data in a single message round trip. For some databases, it will still do like multiple requests for each row. But anyway, you should try to use at least use the API. At least try to use the right API. In JDBC, it's something like add batch. And we actually use our own library that uses like low-level Oracle interface. And we also do this batching by default. So each operation is operation, and sometimes the size of batch is 1. We don't have operations on a single item. And then there's like, this might sound funny, but there's always option to buy a faster CPU and disk. But the key point here is that you need a really faster CPU, you don't need more CPUs. Because the thing is, the faster CPUs will reduce the locking time. Then, of course, you should be careful to design your data structures and database schema. And what you want to do is you want to try to avoid table structure where you have to do absolute updates. At least you shouldn't do them during like transaction processing. The other way is to, instead of updates that most likely are to be blocked, you can use inserts into some like changelog table, and then after a while you aggregate, like calculate the sum of all transactions and apply it to rows once. This is what we do in our batch processing system. So basically we create 1,000,000 entries of transactions, and then we sum them up once, apply the amount to accounts, and we are done. Then, so this is a bit dangerous, but still I think that, so the idea is that some databases offer you a physical row identifier, and it's the fastest way you can access a row in a database. And actually databases use them, those identifiers themselves. Each index consists of the key fields and mapping of these key fields to some row identifiers. So in Oracle it's row ID. I know that Postgres has something called CTID, which is basically the same. So if you modify the same, if you access the same row and same transactions more than once, what we do is that we first get this row ID, and then we use it in where conditions on all other SQL statements. So the next idea is okay, it crashed. Great. So the next idea is to combine SQL statements together. Yeah, I know. I'm launching the application again, so you will see it in a moment. So the idea is to combine the SQL statements together, and you have to go to your database documentation and look for ways for probably non-standard SQL statements that your database supports. Okay, so it's doing recovery. And finish. Okay, so combining statements. What Oracle offers is that you can combine a select statement with any update statement, or actually delete and insert statements as well. So instead of having select and then update, we often use an update that returns some other information that we would usually retrieve with a select. And this is also a good way. So if your application logic allows that, this is a great way how to start like pessimistic locking, to place a lock on a row and then prevent it from concurrent updates. There are also some other things like Oracle allows to combine insert statements into different tables of different data. So the case is that we often have a single transaction and we want to store it into multiple tables. And then what we do is that we use this Oracle feature like insert all, and then just specify like into which tables, which fields to insert. And so it's a single statement. Of course, it performs much faster than 2 statements or 3 statements. And so the kind of like most important trick to avoid holding locks for a long time is to reorder statements. And we have a rule that update statements should be performed last, just before the commit statement. So that's not always possible, but there are often situations where developer simply puts update statement as a first instruction in the program and simply doesn't think about the consequences of that. So what we do, so instead of update and then insert into a table, we usually do inserts first and only then do updates. Then I think most of the databases offer you a possibility to combine a SQL statement and a commit. So this is typically called auto commit. And what we do is if we have like multiple statements, for example, insert, update, and commit, that's 3 different statements. We usually add commit to the last statement. So we do insert, then we set auto commit to true, and then if update succeeds, it commits the data as well. And then there's like a quite extreme case. This doesn't give like a huge improvement, but so basically all the work to prepare the data for the database has to be done before any of the statement is executed. So in Java, it means that if you have multiple statements, you call this setInt, setString, setFloat methods first, and then only then you start to call execute on all statements. And this is actually not an option for some APIs, because Python combines those 2 different steps in a single API call. So it has like execute, you give a SQL, and then the data. And the API we use, we also have like this, we put the data there first, and only then do execute for like 3 or 5 statements in a row. So now this, so last part, how much time do I have? So the last idea is to reduce the lock contention on a single row. So there are a couple of cases where we have to keep counters of transactions and like total amount of transactions in a single row for like, I don't know, single bank. And what happens is that processes all try to take the same lock. So what we do is that we add additional primary key to a table, like it's called usually partition. Actually not partition, because that's a reserved word, but we add some kind of partition. So instead of 1 row, we have like 4 rows maybe 2, maybe 8, depending on how much concurrency is going on. And then in each process we choose which row to update. So instead of contending on one lock and one row, the processes now can choose between like 4 rows and 4 locks. And this gives us like much better performance. Of course, you quickly run into other problems like database is not capable of doing so much operations. So that's all from me. So maybe